Today we are going to learn the inrush current phenomenon in a power transformer. For transformer equivalent circuit we have seen in previous lectures. So this is how it looks like. So here R1 and JX1 is the primary resistance and leakage reactance, and R2 dash JX2 dash corresponds to secondary resistance and leakage reactance, and there is a shunt branch RC JXQ, it is written here. So this is the transformer equivalent circuit. And about no load or exciting current. What does no load current consist of? The current flowing through the primary winding of a transformer when nominal voltage is applied across its terminals with the secondary open circuited is known as the exciting current or no load current. The main flux in a transformer is established by this exciting current, which flows independently of the load current. In an ideal transformer, this current is 0, but there is no ideal transformer, right? So during the steady state operation, the magnitude of exciting current is typically less than 5% of the rated load current in a practical transformer. However, under transient conditions, following the energization of the transformer, the magnitude of the exciting current may reach as high as 8 to 10 times the rated current, or 700 to 900%. So this is how. So around 8 to 10 times it will reach under, the transient conditions during energization. But under no load conditions, it is less than 5% of the, under normal conditions or steady state operation conditions, it is less than 5% of the rated load current in a practical transformer. This is about no load current. Now think about what does this no load current consist of. So if you look at the equivalent circuit, the no load current, for example, this is open, so there is no current in this branch. So only the current will flow through this branch. Okay. And then since the no load current is very small, just 5%, then drop in this component is very small. In fact, the impedance of this shunt branch RCJXQ is very much high than R1JX1. Therefore, more or less, entire voltage drop will be across this shunt branch. So here, of course, the no load current passes through this R1 also, JX1 also, and then RCJXQ, right? So what is R1? R1 actually majorly it consists of the winding resistance. So winding resistance loss will be there. What this RC will represent? RC is actually the not a real resistance. It is a fictitious resistance. It represents the losses in core, eddy current loss, and then hysteresis loss. In general, complete loss it represents under no load conditions. But what are the complete losses that under no load current the transformer will face? Now you see, you have to consider both electrical and magnetic systems. So if you consider electrical system means, there is a wire, the primary winding. The winding is, isolated from the core with an insulation, dielectric material. Therefore, the winding and core will act as two electrodes, and there is a dielectric between them. So definitely that will act like a capacitance, right? So of course, distributed capacitance, you can consider overall capacitance. There will be certain capacitance between the wire or winding and the core. So there must be some dielectric losses associated with that. So there are dielectric losses. There are losses in the conductor. Of course, no load current will flow through the wire only. So there are losses in the conductor, and there are losses in the magnetic part also, that is hysteresis and eddy current losses. So these four types of losses are predominantly occurring in the transformer under no load. But out of these, what are dominant? The dominant components are hysteresis and eddy current losses. Therefore, that are called core losses. That's why RC more or less represents hysteresis and eddy current losses. Of course, all losses are when you operate the transformer under no load. Obviously, all losses will be included in the RC. That's what it will happen. So, because the calculation of RC is based on no load test, right? So, therefore, the whatever value calculated at rated voltage and all. So, the corresponds to hysteresis losses, eddy current losses, and whatever losses occur inside the transformer. So, this is about the no load current. And no load current under transient conditions, when switching on, switching off, so it may reach as high as 8 to 10 times the rated current, not the value of rated no load current, rated current of the transformer. So, no load current under steady state operation is 5% of the rated current, but at the same time under transient conditions it is 8 to 10 times the rated current. Next, components of exciting current. The exciting current consists of two components, loss component IC and magnetization components I5. So, you can see here, this is the loss component IC, and then this is the magnetization component I5. The loss component, which is in phase with the applied voltage, accounts for no load losses. Already I have explained what are all the no load losses are. The magnetization component lags the applied voltage by 90 electrical degrees and is responsible for producing the main flux of the transformer. So, the transformation, whatever is happening in the transformer, is not happening without any current. It is happening due to this magnetization component. It must be there as long as we need a transformation. Therefore, magnetization component will continue to flow irrespective of the load. The load MMF is in fact countered by the equivalent MMF from primary side also. So, whatever current is drawn at the load, whatever magnetic field is produced by that is countered by the primary additional current, but this current will always flow irrespective of the load. This current will always flow because there should be magnetization always. So, magnetization current will be there. It is different and independent from load current. Now, the last component. So, here it is presented here, pictorially. So, there are flux lines. So, the changing flux inside the core will have certain characteristics known as hysteresis. So, the hysteresis means, here the path of the magnetic, flux versus magnetic field intensity is not same. So, the concept came from the fact that it appears that it remembers the history. But of course, remembers the history means, once it is fully saturated like this, and then when you are going back, it will not trace the same path, but it will be a little bit higher flux will be there. And even when you when the current is 0, means when H is 0, still the flux will be there. That is what is known as residual flux. So these alignment and de-alignment of magnetic dipoles will take place due to these flux reversals. Then due to these alignment and de-alignment, there will be associated energy loss in the magnetic portion of the circuit. That is what is known as hysteresis loss. And whenever the flux lines are going through a metallic portion like this, then there will be currents associated with these flux lines, which will be opposing the original magnetic flux, producing them. So these currents are known as eddy currents, and eddy current losses will also, due to the flow of this eddy current losses will be taking place in the transformer core. So this is about the last component of the transformer no load current. Now the no load losses include the core losses, hysteresis and eddy current losses, dielectric losses. Just now I have explained to you. The winding and the core form a capacitance with the insulating medium separating them. So there will be associated dielectric losses, of course negligible, but they will be there. And ohmic losses due to exciting current. The exciting current has to flow through the winding. Therefore, associated I square R loss will be there. That is ohmic loss due to exciting current. Of these, the core losses are predominantly insignificant. That's what is I have pointed out. The core losses depend on the operating frequency, the saturation characteristic of the transformer core, the rated maximum flux density, thickness of the laminations. So these are the main factors on which the core losses depend. So please remember, it is not the ratings of the transformer on which it depends, but it depends on the maximum flux density, operating frequency, the saturation characteristics of the transformer core, the thickness of laminations, and so on. So the hysteresis loss results due to energy dissipated in magnetization and demagnetization of the magnetic dipoles in the core in response to the applied voltage or magnetic field intensity, while the resistive loss due to flow of the induced eddy currents in the core causes the eddy current losses. This is what we have discussed. The core losses may be approximated by the following expressions. So these are empirical constants, KH and KE are given here. So hysteresis loss is proportional to frequency and Bmax to the power of X. X is typically 1.6. And the eddy current loss is proportional to frequency square, thickness square and Bmax square. Bmax is maximum flux density in the transformer core. So where F is operating frequency, Bmax maximum flux density, T thickness of laminations, KH, KE and X are the constants which depend on the core material actually. So these are about the last component of the no load current, and then quantitative analysis of exciting current. So here if the secondary is open circuited, so I2 dash is 0, means this portion is not there. You can simply delete this portion, and then you have only R1 JX1 in series with parallel combination of RC JXQ. Now I1 is equal to I0. Yes, this is no load current. The primary current is equal to I0. Then V is equal to I0 Z1 plus E. But since Z1 is also very small compared to RC JXQ parallel combination, and I0 is also very small, this component can be neglected. So neglecting the drop across the primary leakage impedance, E is approximately equals to V1, the applied voltage, right? So the induced EMF E equals to N1 d phi 1 by d phi by dt. Thus V1 is equal to N1 d phi by dt. Of course, neglecting the losses. So V equals to N d phi by dt. Therefore, the relation between phi and V is, if phi is sinusoidal, V must be sinusoidal. Or V is sinusoidal, phi must also be sinusoidal. Please remember, it is not the no load current which is sinusoidal. If you apply sinusoidal voltage, the current need not be sinusoidal, as we will see soon, but the flux need to be sinusoidal. So this is what this analysis will give us. Now, qualitative analysis of exciting current continued, assuming a sinusoidal supply voltage V1 equals to some V maximum sin omega t plus lambda. Therefore, V1 is equal to N1 d phi by dt. Solving the above equation, we will get phi equals to minus Vm by omega n cos omega t plus lambda plus some constant k. So here actually we have ignored the lossy component of the current voltage drop. So if we include that also, the k will be actually a function of time, which will be decaying with time. So at t is equal to 0, k will be having certain value, and then as time passes on, that will diminish and become 0. Under steady state, this term k will not be there. So that's why here for some it is written as some transient portion phi of t. We will soon see what it is exactly. So therefore phi equals to minus phi m cos omega t plus lambda plus k. We using this derivation. So the first term on the RHS denotes the steady state main flux, this one, of the transformer, while the second term denotes the transient flux, which depends on the supply voltage and residual flux at the instant of energization. This we will see soon. This term decays to 0 at steady state. This is what it is. So here the decaying portion is not actually seen from the differential equation. So a constant term will come actually. But the term will decay with time due to the reason that there is some lossy component associated with that. That we will soon see. Now, it is therefore seen that the steady state flux in the transformer is sinusoidal. Please remember, if the applied voltage is sinusoidal, it therefore follows that the magnetization component of the exciting current, which produces the flux, should also be sinusoidal. But however, it is not so. Therefore, the exciting current which produces the flux is not actually sinusoidal, that we will see. Flux is sinusoidal because voltage is sinusoidal. It needs to be, because there is a relation, direct relation between flux and voltage. So flux need to be sinusoidal if voltage is sinusoidal. But whether current need to be sinusoidal or not, no, current need not be sinusoidal, that we will show soon. The economic operation of a transformer dictates working the core at the curved part of the saturation characteristics, and thus the magnetizing component of exciting current and flux are non-linearly related. See, if there is a linear relationship between I and phi, then if flux is sinusoidal, then I also should be sinusoidal. But there is no linear relationship. Why? Because the core operates at the curved portion of the saturation characteristics. So this is the magnetization characteristic. So around here it operates. That's the reason the relationship between this is phi or flux density B, this is H or current I. So the relation between I and phi or H and B is nonlinear. Therefore, even though phi is sinusoidal, I will not be sinusoidal. That's what it implies. How, we will see soon. How to find out the current also we will see. This introduces actually harmonics in the magnetizing current, whose waveform assumes a peaky shape with respect to time. Now, qualitative analysis of exciting current. So here applied voltage and flux, just now we have seen there is a differential operator relating flux and voltage. Therefore, they must be 90 degrees away from each other. If voltage is sin omega t, then flux will be cos omega t, like that. So here the voltage waveform and current waveform, this is the exciting current waveform and voltage waveform and flux waveform are given here. So here you can see applied voltage is sinusoidal, then steady state flux must also be sinusoidal, and it is lagging behind the voltage by 90 degrees. You can see this is pi by 2. Okay. So typically this is the voltage and flux waveform. This has to be maintained now under steady state. Now for this to happen, what is the current? So current waveforms are given here. So for a hysteresis characteristic like this, then you will have a current characteristics like this. This is how the current looks like, but how it is to be plotted and all we will see. So this is the voltage waveform. This is voltage waveform. This is flux waveform phi. So within the flux waveform, you can see this is a peaky nature of the current that will occur. Why this will occur and all we will see just now. Here it is given the graphical method to obtain magnetizing current neglecting hysteresis. So this I will just plot in the next graph. Here. So let us see how they are related. It is to be done very systematically here. So neglecting hysteresis. Neglecting hysteresis, the BH characteristic or phi in I characteristic. So this is I, this is phi. The characteristic will be like this. And in the negative cycle, like this. What is to be done? How to plot the waveform of current? Now let us draw the flux waveform. Flux waveform, this is flux waveform, please remember. This is not the voltage waveform. Voltage waveform is 90 degrees leading to this flux waveform. Now this is my flux waveform with time. Okay. Now let me divide into several time instants like this. Now this is the nonlinear relationship given here between phi and I. This is BH characteristic, of course. Phi is related to B, I is related to H. Okay, simply some constant multiplication will give you B, and another constant multiplication will give you H from I. Therefore, this I and phi, H relationship. Now we have to obtain, we know phi waveform, which is lagging the voltage waveform by 90 degrees. And from this phi waveform, phi with respect to t, we have to obtain I with respect to t. Means for a sinusoidal flux to be in the transformer, what is the nature of the magnetization current? That's we are going to find it out. The magnetization current follows the hysteresis characteristics. Therefore, we have to use hysteresis characteristics to obtain the magnetization current. Now here on this axis, I will take here time axis t. Just it is independent from this BH characteristics. Please, just I am cutting the BH characteristic here itself. Now I am plotting my y-axis here, which is current, because I need an axis parallel to this I-axis of hysteresis, and here this flux axis is parallel to this flux axis of phi t characteristic. Now from phi t I will obtain IT characteristics. Now what is the way? The way is simple. When it is 0, what is 0? When flux is 0 at a time t is equal to 0, this corresponds to 0 flux here. That corresponds to 0 current also. Therefore, my first point is here. Then the second point. At some instant t is equal to t1. So this is my flux, and for that particular value of flux, just trace it on the phi characteristic, and this particular value of flux, this is the current. So this current I have to plot on this, and this corresponds to t1 instant. So therefore I have to actually mark the instants here: 1, 2, 3, 4, 5, 6. How many are there? 1, 2, 3, 4, 5, 6, 7, 8. 7. Extend a little bit. 8. Okay. Now this is my first point. Then for the second point, this is here, and this flux traces here, and corresponding to that, at second instance you have to plot like this. Then third instant, time instant. Now we are in the saturation portion of the BH characteristic. Therefore you will observe a peak in nature here. So this is how, and then the peak then again like this, like this, like this. You go on plotting, it will end up here. So this is how the magnetization current will look like. So you can see clearly when you are having a sinusoidal flux, and you will get a magnetization current of peak in nature. So if I plot on the same curve, the magnetization characteristic will look like this. Now here actually what is neglected here is the hysteresis is neglected. It is coming like this. Right. So you have seen the graphical method to obtain magnetizing current neglecting hysteresis. Now if hysteresis is also considered, so considering the hysteresis, the same characteristic actually So you have to plot the hysteresis characteristic like this. So it will go, and then I have to redraw this one. Sorry, it is. Now it will go up like this. This is how hysteresis characteristic will look like. Now here again same manner, flux waveform I am drawing, which is 90 degrees lagging with respect to voltage. This is flux waveform. This is phi t. Now to obtain the current waveform from this, so here the current waveform, divide these instances into several time instances and then trace this. So how it will go? So this is very important actually, the characteristics. This is while going up actually. Going up means when the flux is increasing, this is the path, and then when the flux is decreasing, this is the path. So at time t is equal to 0, flux is 0. At time t is equal to 0, flux is 0. This is, the flux is going up now, right? In sinusoidal portion, it is going up. Therefore, this point corresponds to this point. Let me use different ink tools. I'll use this ink. So this point corresponds to this point. I'll use this ink. And this point corresponds to, at t is equal to 0, this point. Now let me draw the time scale. 1, 2, 3, 4, 5, 6, 7, 8, something like that. Now you can see it is not starting at 0. This is current I. This is time t. It's not starting at 0 because at 0 flux corresponds to non-zero H or I. This is phi or B. Okay. Now then the second point corresponds to somewhere here, and this corresponds to here. So like this if you draw, then you will end up in a curve like this, and then it is important that when it is reaching certain value, this value say in the downward portion, so just before this instant, just before, one instant before it is, the flux is becoming 0, you can see the H or I has already become 0. So here this will end up like this. So this is actual flux 0 position. This is flux 0 position. There the current is already becoming negative. So here you can see this is flux 0 position, and for this flux 0, this corresponds to here, this point, that is somewhere here. Okay, so this is how the curve will look like, the peaky nature, but it is displaced from the phi characteristics. So here I will draw on this itself the magnetization characteristics or current. So this will look like this one. Both are on different scale, means I also on this scale. So you can draw anyway. This peak can be inside, outside, it doesn't matter. So don't take it wrongly. So this is how it will look like. So again it will reach peak in the negative, and then like that it will continue. This what is shown actually few slides before. You can see here exactly. So since there is a BH loop here, so it is not 0 here, and then it becomes 0 before the phi curve. This is phi curve. This is phi curve. Before the phi curve becomes 0. So this is how the exciting current under no load steady state will look like. Please remember, until now we are dealing with steady state currents only. So this is the graphical method to obtain magnetizing current considering the hysteresis. Now next is inrush current phenomenon. Inrush current, actually inrush current is also related to magnetization current only, but it is under transient condition, means sudden switch on and all. So the steady state exciting current we have seen. Steady state means under normal operation, if it is under either no load or even under loaded also, exciting current characteristics we have seen. Of course, under loaded condition, the percentage of this exciting current is very less, so it is negligible. But under no load condition, it is the only current, apart from the core loss component. So it will be dominating only in that conditions. So, but in the transient conditions, means whenever switching on the transformer takes place, then there will be inrush phenomena. Huge current will flow, which is around 10 times the rated current itself. So 5 to 10 times. So that what is that part of the current we will see. When a transformer is first energized, a transient exciting current flows to bridge the gap between the conditions existing before energization and the conditions dictated by the steady state requirements. In every phenomenon, so in any circuit or anything, any system, if there is a steady state operating condition and you are switching on, when you are switching on the system, if you are switching on in such a way that the steady state conditions are not disturbed, then there will be no transient radar. Or you are switching on the system at its natural zero, then there will be natural zero, means it is phenomenon, not voltage zero or current zero. Don't go by like that. So it is related to energy actually. So at that instant, if you switch on, there will be no problem. That what is that instant we will see soon. But if you disturb, means if you are switching in a different position, then some transient will arise within the system and which will adjust the system to steady state, and until that the transient will be lost. Of course, the transient is associated with some losses which will eventually make it die. So this is how the response will be. Even in transformer case also, a transient exciting current flows to bridge the gap between the conditions existing before energization and conditions that are dictated by the steady state requirement. So this is what will happen. As discussed, there exists a transient component of flux which depends on the instant of energization and residual core flux. So, yes, the magnetization component of the exciting current associated with the transient flux is known as the inrush current, which eventually dies out. Oh. The shape of the inrush current curve characteristics is similar to that of steady state magnetization current time curve, that is peaky in nature. However, the magnitude of inrush current is incredibly huge, which is of course governed by the energization conditions. So these are the typical values actually of exciting current as well as inrush current is given here. See, as a percentage of full load current it is expressed here. Here it is expressed in per unit values actually. So you can see 3.7 for 2.5 kV voltage class, 3.7 to 3.3 percentage. Percentage means if you express in per unit, 0.03 is the exciting current, means no load current. More or less no load current, the magnitude of no load current. You can see around 3.9 percentage, means 0.039 per unit values only. That is the value of exciting current. Now, if you see the inrush current, this table gives a inrush current. The inrush current can be seen to be around 5 to 8 times or 4 to 7 times in core form of the transformer, and shell form of the transformer it is 2 to 4 or 2.5 to 5. So the reason is the impedances are different in case of shell and core form. So this is how the inrush current magnitude will be in a practical transformer. So now what is the inrush current phenomenon? Inrush current waveforms we will see how to draw that. Now we have seen the exciting current characteristics. Now what is inrush current? Now let us see the transformer is operating like this. So if this is the normal operation of this is the flux characteristics, flux which will be 90 degrees lagging with respect to voltage. So you have to imagine what is the voltage. So this is the flux characteristics. Now suppose it is operating under a normal steady state, then there is no sorry, I will take red color, this one, right, this one, yeah. Now the exciting current characteristic will be like this actually, and then it is becoming 0. So like this, then it becomes peaky again, and then becomes so if I continue red color, sorry, blue color. So if this is the flux waveform, okay, now corresponding to it there will be inrush current also, sorry, excitation current also, like this. This is the waveform. Suppose I switched it off, when the current becomes 0. So here I have switched it off. Then what will happen? The flux is having certain magnitude. Will that say change? This is actually residual magnetism. When the current becomes 0 also, there will be certain magnetic flux. So of course, it is in this graph, it is becoming huge, but normally it is not of that level. Small residual flux will be there. So I'll take blue color for representing the residual flux. So the flux, when the current becomes 0, the flux is here and it continues. I switched it off. Then it continues like this, the constant flux. Then what happens to the current if I switch it off at this instant? This instant, switch off. Current will be 0 because I have switched off at current 0 and it continues. There is no current, so current waveform will continue like this. I will take red color now. So current waveform will continue. Suppose when the flux is in the negative max, this is actually, this peak should coincide. When the flux is actually, I have switched it off here itself, but this is on the sinusoidal, this is voltage waveform is there. No? So again if I switch it on at this instant where the flux reaches negative maximum, means as per the steady state, if it continues in the steady state, this would have been the situation. So it would have been at its negative max, that B is at negative, phi is at phi max, again minus phi max. So this is plus phi max, plus phi max. So I switched it off at a current 0. Then the actual flux is continuing along this, right? Now suddenly I switched it on at phi is equal to minus phi max, means now it is not minus phi max, it is this phi residual actually, phi residual. So this is the value actually. So at this instant I switched it on again. So what will happen? Because I switched it on means what is the corresponding value of voltage? This is voltage is 0, right? It is 90 degrees. Flux is at 90 degrees, means voltage is 0. So at that instant I have switched it on. Then the flux has to follow this kind of slope in order to have the follow the voltage, because voltage is sinusoidally changing. Okay, I switched it off at this instant, but voltage is continuing. Now I switched it on. The voltage waveform still continues, but inside the transformer, the voltage, the induced voltage has to balance with the applied voltage. E must balance with V1. So, which is d phi by dt. So, thus d phi by dt means slope of nature of slope of flux should follow the original characteristics like this, the sinusoidal this one. Then only it will balance the voltage. So but flux is at this instant, the value of the flux is 5 residual flux. Now here onwards, unless it follows the similar slope characteristic, the voltage will not be balanced. Therefore, what will happen? The flux has to follow the similar slope characteristics. So, from where it is currently? It is currently at phi residual. It is not at minus phi max. the flux inside the transformer is residual flux. Now from there it has to start and follow the same slope characteristics. Means if you differentiate, the same voltage should come, whatever applied voltage is there. Therefore, the waveform that has to be followed by this is given by, from here phi residual it will start, it will follow exactly the previous waveform slope. I don't know whether I have drawn properly. Yeah, this way. So this is how the flux has to follow. Unless it decays, it must decay over a period of time. So it will follow like this. You see how much the flux is increased. So here if you compare, so this is, what is this magnitude? This magnitude is minus phi m and this magnitude is phi residual. Okay. Therefore, if there is no decay in the flux, then this is again phi max, right? Phi max. And if the decay, this difference continues to be this, same as this phi max plus Rs. So, total difference is phi max plus phi residual. E is the difference here. So, this difference if it continues, then the peak value of the flux is, this is phi max plus res. So, this is peak, phi peak is 2 phi max plus phi residual. If it did not decay, of course, there will be reduction in the flux due to losses in the magnetizing portion, hysteresis, eddy current, etc., and some winding losses, etc., will reduce this flux. But if it does not decay, suppose it does not decay, so if it reduces but it doesn't become almost zero, it is almost this much only. The reduction in one cycle is almost negligible only. So 2 phi max plus phi res is the peak flux. Now you can imagine the how much the inrush current will be. Inrush current means after switching on, what is the current characteristics. Therefore, this amount of flux has to be met by huge current actually. BH characteristics, right? BH character, this is I, this is phi. Now, if your phi value is too much, then you will end up somewhere here. So, then the corresponding I value is also huge. If it is here, then the I value is here. But if it is in the saturation portion, if it is 2 phi max plus phi res, then huge current will flow. Therefore, the current, the inrush current will be huge compared to the steady state current. Now this inrush current from here, it will follow and then huge peak and then come like this. So it will continue. So this is how the inrush current will be very high in magnitude compared to the steady state value of the inrush, so an excitation current or even steady state load current also. It is around 8 to 10 times, means you can imagine the peak value of the current. Okay, now here one instance is shown here where I have switched off the current at its current 0 when the flux reaches phi residual flux. What happened? Drawn has gone. Okay. So you have seen the we have drawn the waveform at current 0 where the flux is reaching the residual flux, and then we have switched it on the transformer when the flux is its negative maximum, means when the voltage is at 0. So if you switch on like that, huge inrush current has been shown. So due to the flux requirement of that is phi is the peak flux is around 2 phi m plus phi r, so phi peak. So this is how the inrush current waveforms will look like. Now let us go through the phenomenon again, the inrush current phenomena. So this is V of t is equal to Vm sin omega t plus lambda. Let us take the voltage to be Vm sin omega t plus lambda, means certain phase angle. Now phi of t is differentiation of that plus some constant k. That k is actually phi t, the transient portion, the steady state portion plus transient portion. Now case 1, the transformer is energized at the instant where supply voltage is at its maximum. Therefore, there is no residual flux. See, if the supply voltage is at its maximum and there is no residual flux, so in this case, residual flux is neglected. And supply voltage is assumed to be at its maximum. When supply voltage is at its maximum, then flux is at its 0, right? So substituting this, 0 is equal to 0, then k is equal to 0. So in this case, the transformer flux starts out under normal conditions and there would be no transient at all. So because the flux is 0, from 0 it will start, therefore there will be no issue at all. So there will be no transient, and residual flux is also neglected, so it will be same way actually. Now this case 2, the transformer is energized at the instant where the supply voltage is 0 and there is no residual flux again. So in this case again there is no residual flux, but if the supply voltage is 0, then flux will be at phi max. In this case, the total flux consists of sinusoidal flux plus a DC flux and reaches a crest equal to twice the normal flux. That's what, just now we have seen. 2 phi m plus phi r. Now in this case phi r is not there, therefore it will be just 2 phi m. And then case 3, the transformer is energized at the instant where the supply voltage is 0 and the residual flux is around 60% of the maximum rated flux. Of course it is exaggerated. So in this case, if you equate that one, then phi of t is equal to phi m cos omega t plus lambda plus 1.6 phi m. The k becomes 1.6 phi m. So this case we have already seen that the waveform that is drawn is of this only. Okay. Then let us see the waveforms here. Yeah, here they are given here. Transient flux characteristic is given. See, this is when the flux is at negative maximum under steady state. This is steady state flux. So if we switch on at this instant, see negative maximum, switch on. Flux is, the residual flux is neglected, therefore in the transformer just before switch on, 0 flux is there, that is what is assumed. This is case 2. Case 2 means 0 flux is assumed. Then of course some residual flux will be there, it will start from a little bit different, that's what we have seen. So if it is, we have drawn the waveform, no? That's what I was talking about. Now in this case, it starts from 0 and it has to follow same slope as the steady state slope. So here the steady state is going like this. Therefore, it has to follow the same slope, because differentiation, if you differentiate, it should become the voltage. So some constant plus differentiation is also have same slope. That's how it will happen here. This constant is this much. So that this constant plus the same waveform. So the waveform will be shifted. The flux waveform will be shifted like this. So it has a severe consequence. When flux waveform shifts, the current waveform will not shift linearly. The reason is, when the flux is increasing beyond a certain value, it will have nonlinear relationship. It will have very huge current flowing through the system. Therefore, for this 2 phi m, then a huge current will flow inside the transformer, and then the current will be peaky in nature, and a huge magnetization current will flow like this. And similarly, in this case, certain residual flux. This is what actually we have drawn. In this case, certain residual flux is already there, and then it is going through the negative maximum when we are switching on. This is the steady state characteristics. Okay. So this is supply voltage is also given here. Supply voltage and flux is always 90 degrees. Supply flux is lagging supply voltage by 90 degrees. Now here same slope has to be there when you switch it on. The flux should follow same slope. So therefore, but it is at residual flux at this position. So it must follow the same curve with same difference like this. So the difference between this dotted curve and this curve remains same. So it will follow these characteristics. You can see total flux is huge flux again. So again, therefore, the current will be huge peak like this if you draw it from magnetization characteristic. This is case 3, whatever is just discussed just now. Now, typical inrush current waveform. Following the same graphical approach, we can approximately obtain the waveform of inrush current from the obtained flux waveform. Although the maximum flux is only twice its normal, the current reaches a value equal to many times because it is non-linear. Flux is just twice, but current is not just twice. It is several times because of the nonlinear characteristic or saturation characteristics. It is because of high degree of saturation of the transformer magnetic circuit. So this is how it is shown. So you can see just from flux how to obtain. Actually, there is some issue here. So we are taking entire flux to be flowing through the core only, but it is not so. Some flux will be leaking. Some flux will be leaking through the air actually, because after core saturation you cannot increase the flux inside the transformer core anymore. So additional flux has to be met from leaking paths through the air only. So that portion we are, for the time being, we are neglecting, assuming that the entire flux has to flow through the transformer core only. In that case, the saturation will go on, we will be entering into the nonlinear portion. So this is the total flux, and maximum flux is when 2 phi m. So actually when it is phi m, this is phi m, see, this is phi m. When it is phi m, it is almost in the linear portion only, of course still non-linear. But when it is 2 phi m, you see we are ending up somewhere here. So this is huge value of current. I is huge. So this corresponds to this peak actually. Okay. Of course here, as I told you, we are assuming entire flux is flowing through the core only, and the core is saturating even further. But actually some portion of the flux will go through the air after certain level of the flux inside the core. So this is how the typical inrush current waveform can be obtained. Inrush current can be found graphically. Now generalized analysis of the inrush phenomenon. Until now we have assumed the resistive portion is not shown to you, but there is actually resistive portion. Why resistive portion will arise? Because here the resistance, this resistance Ri is given like this actually. Okay, so it need not actually represent only the winding resistance loss, please. It represents the core loss, eddy current loss as well as winding resistance loss. This is approximate analysis. An equivalent circuit can be imagined for an inrush current phenomena. For inrush current phenomena, so inrush current will have some loss in the winding also. Core loss will be there, and even eddy current. A core loss means hysteresis loss will be there, eddy current loss will be there during that time. Therefore, all these losses I am representing by some resistance R in series with it. Of course, in the equivalent circuit, it is a different representation. One, the core loss component is in the parallel to the inductance, and then the core loss, the winding resistance is in series. But here I am representing the overall loss in the transformer. I am representing with some R in series. Then some inductance L associated with the magnetizing circuit and all will be there. So V is equal to Ri into L di. Ri plus L di by dt is the circuit characteristics, right? Now which is equal to Vm sin omega t. Now here I can solve this for I and then come up with this a solution. But the problem here is the L here is non-linear. It doesn't follow same relationship with I. So L changes with I. Therefore, the solution will be complicated, and I, magnetizing current I, is peaky in nature. It is not sinusoidal. Therefore, solving this and then finding out the solution in terms of sinusoidal will be erratic. So better to have a relationship in flux, an equation in flux. So therefore, this equation can be converted in terms of flux using this. L di by dt is equal to N d by dt, or L is equal to N phi by I. Thus, what will happen? The equation gets converted into V and phi in this manner. Now, V is Vm sin omega t. So, therefore, this equation again simplifies into this. V is equal to R phi by L, d phi by dt, Vm by N. With this manner, what is happening now? So, the error is just in the time constant e to the power of minus t by tau. Some time constant will come. The error is just in the time constant, but waveform will not change. Wave shape will not change. The flux wave. So just time constant will be different. The time constant means what? So the decay characteristic may be different, but nature of the wave will remain same. That is one advantage of using this kind of equation. So in flux, so it is better to use equation in flux compared to current. That is very, very important, because I is peaky in nature, phi is sinusoidal in steady state, right? So even in the transient characteristics also, we find using flux is better compared to current. Therefore, this equation is taken here. So R by phi, when you solve this, the phi becomes the transient portion, that is natural response. When equated to, if this portion is equated to 0, then that is called natural response. Natural response is phi equals to A into e to the power of minus t by tau. So that's what, in the beginning, what we have considered as a transient portion, its exact waveform has been given here. Therefore, the value of transient portion is A into e to the power of minus t by tau. Of course, A may be calculated using the resistor supply voltage at the instant of energization, as of course this we will not use now, because let us go to complete solution, then obtain the value of this one. Now here this is the steady state solution here. Steady state solution, simple sinusoidal analysis you can do, and then phi, value of phi can be expressed as Vm by n divided by root of r square by L square plus omega square into sin omega t plus lambda minus tan inverse omega L by r. Of course, this value is approximately equals to 90. So instead of sin omega t plus lambda minus tan inverse this thing, this can be simply replaced by minus cos omega t plus lambda. Okay, so that's how it will end up. Of course, this maximum term will be there here. Okay, so here even that resistance portion is neglected compared to the capacitance. Then this becomes Vm by just let us go back, Vm by omega n, same. So minus Vm by omega n cos omega t plus lambda. Or minus phi max cos omega t plus lambda. So simply you write minus phi max, because this is corresponds to maximum value of phi, cos omega t plus lambda is the steady state portion, and transient portion is simply some a e to the power of minus t by tau. Okay. So this total solution is the combination of these two. So the approximate solution, this is the exact solution by the way, approximate solution is a e to the power of minus t by tau. Tau is again r by L only here, so L by r, plus minus phi max cos omega t plus lambda. So at different instances we can find the value of a. Okay, so for example at t is equal to 0, if flux is 0, suppose if phi is 0, at t is 0, if phi is 0, then a becomes a equals to what? Is equal to 0 if you substitute, and if you make the flux is 0, a is equal to phi m cos lambda. Okay. So then phi equals to phi m cos lambda e to the power of minus t by tau, and then minus phi m cos omega t plus lambda, right? When omega t becomes, when lambda is nearly 0 and when omega t becomes pi, then this value phi becomes roughly 2 phi maximum. This is what we have seen. And if residual flux is also included, means when t is equal to 0, if phi is not equal to 0 but it is equals to residual flux, then you will get phi max, phi peak is equal to 2 phi max plus phi residual. So this is how the maximum flux will reach this value, 2 times phi max plus phi residual under inrush current phenomena or during the transients. The generalized analysis of the inrush phenomena. Just 1 minute, I have to. So here, what is assumed is the decay is not that much. So until omega t becomes pi, if this transient decays, then there will be nothing, right? So, but it is assumed here that the decay is not that much. Means the losses that are occurring in the core and then windings or insulation are not that high to decay this waveform very fast. In that case, if negligible decay is there within omega t is equal to pi, then in that case you will get this 2 phi max plus phi r. Right, this is how the residual flux will be higher than, the flux will be higher than the maximum flux under steady state operation, which is leading to very high inrush current. Now, what is the practical value? So, practically, the maximum value of phi during the inrush current phenomena is some k times phi maximum. That k value is 1.6 to 1.8. This is the practical range of the flux inside the transformer during the transient conditions. So then the inclusion of losses results in a decay in the magnitude of inrush current, and eventually the transient dies out, because transient starts with t is equal to 0, and since e to the power of minus t by tau is involved, over a period of time this becomes 0, therefore the transient portion dies out, and only steady state magnetizing current is peaky, but which is much lower in magnitude, that will remain. The transient has a rapid decrement during the first few cycles and decays more slowly thereafter. The damping factor R by L for this circuit is not constant. This is very important. R by L changes with time. So we have avoided the this nonlinearity in our differential equation by simply taking phi instead of I. But the nonlinearity will enter into this tau. Means that tau will change with time again. Of course, to that extent it is a little bit inaccurate, but otherwise the accuracy is good enough. But you have to remember that the time constant is not constant, but it changes with time also. And also the transformer inductance with saturation, that is the reason actually. Now this is the generalized inrush current phenomena. Now let me draw the waveforms of this inrush current phenomena, how the flux will look like and all. So the flux wave will look like this. It is sinusoidal, of course, decaying like this, and corresponding inrush current will be peaky like this. Of course, it will decay with time like this. And if you draw for 3 phases, if this is the inrush current in one of the phases which is decaying, the other phase could be negative like this, and the third phase could be having small positive value like this. So in a three-phase transformer. So if you consider three-phase transformer, always one of the phases may be close to a condition where the negative phi max is going on. So therefore the induced current will have a high component always in one of the phases. So this is how the induced current will be there in the transformer. And for calculating the induced current practically, what we have is, let me clear itself, here itself, just wait, erase all, and then take the current. Now, the value of flux during the inrush or transient period is around k times phi m, we have seen, and the value of k is from 1.6 to 1.8 practically. Now, how this k phi m is met? This k phi m, so entire this k phi m need not be from the transformer. In fact, it is not from the transformer core, not flows through the transformer core. Therefore, some portion of the flux must flow through because beyond certain value of flux, increasing the flux becomes difficult in the core. Therefore, the flux must be met because the voltage is there. Voltage has to be matched by the flux. So the flux must be met by the non-magnetic path. Let us call that as phi n. So the k phi m consists of two factors. One is flux flowing through the iron and plus flux flowing through the non-magnetic part of the core. So in terms of flux density, if we say, so this is apparent flux, you can say. This is apparent flux. So BA, let us say, BA into AI, it is iron cross-sectional area. So apparent flux density into iron cross-sectional area is the actual flux, which is equal to again core flux density, iron flux density BI into AI plus actually you can use BS also, saturation flux density is also same, plus air flux density into AN, non-magnetic path flux density into non-magnetic path cross-sectional area, some equivalent value. So if we assume like that, then BA equals to BI plus BN into AN by AI. Okay. Then BI equals to BA minus BN into AN by AI. This also can be written as BA minus BN non-magnetic path, which is linear actually, equals to mu naught times H if you substitute, minus mu naught H into AN by AI. This mu naught AN by AI is written as tan theta mu naught AN by AI. So this is mu naught into AN by AI is some constant which is tan theta. Therefore this becomes BA minus H tan theta. So it is Bi equals to iron flux is equal, flux density equals to Ba minus Bh tan theta. So if you go to hysteresis characteristics, so this is neglecting the neglecting the hysteresis and this BH characteristic. If you go, this is how the characteristic will look like. Okay, on this H tan theta, see Bi equals to Ba minus H tan theta is a straight line, but Ba and H are related by nonlinear characteristics actually. This is how BH characteristics will look like. Then what is to be done is, you have to draw with tan theta as slope from origin like this. This is theta, where tan theta equals to mu naught an by ai, and then identify the Ba, apparent flux density, which can be calculated using this one actually. Ba is simply k phi m by ai. K phi m by ai is Ba. So locate Ba here. This is Ba, right? And this is minus H tan theta line. So a parallel line if you draw here, okay, this will meet, this is parallel to this H tan theta, this is H tan theta, minus H tan theta rather, and it will meet a particular value, this BH characteristic. This is actually iron flux density in the iron. So this is how the iron flux density can be found. Remember here, so if you take Ba entirely due to the iron only, then the current value estimated will be somewhere here. Okay, it is very huge. But because of the some flux goes through the non-magnetic path also, actual H is of less value. So this is the actual current corresponding to or H corresponding to Bi. So this is how the estimation of magnitude of inrush current. Now corresponding to this, now once H is found, after finding H, you can estimate the value of current, because H into H is equal to N into I. H means length of the magnetic path is equal to N into I. From this inrush current peak magnitude can be estimated by H into H by N. This is how, using the hysteresis characteristic, we can estimate the value of inrush current peak. And empirically, practically, what it is actually, approximate values can be found using the, I will give you the next this thing, ink tools, eraser. Yeah. Now, approximately, what is the maximum flux inside the this thing, transformer? So we have seen 2 phi m plus phi r, right, is the maximum flux. Okay, so this is empirically in the order of 1.6 to 1.8 times the maximum flux, of course, but highest maximum possible is 2 times the phi m plus phi r. Now 2 times phi m plus phi r having two components, one is phi iron plus phi n. Now here the maximum flux density in the iron or saturation flux density is normally known. So that's from that let us convert this equation in terms of flux densities. If you convert that into flux density, so this is 2 Bm Ai plus Br again Ai equals to B saturation, because iron is saturated under these conditions. So B saturation flux density into A iron again, plus this is B N non-magnetic portion and AN, this non-magnetic portion equivalent area. Now divide this by Ai. So 2 Bm plus Br equals to Bs plus Bn again mu naught H into An by Ai. Right? From this, value of H can be estimated as 2 Bm plus Br minus Bs into Ai by mu naught An. So this is the value of H that is estimated, and you know the magnetic flux density, based on the magnetic flux density, the maximum flux density for rated voltage, it is fixed actually. It is in the order of 1.1 Tesla to 1.4 Weber per meter square, and then Br is around 30% of Bm, right? And B saturation flux density is in the order of 2.2 to 2.5 Weber per meters. Okay. So after finding the value of H, using the relation just now told, I can be estimated H into H by N, number of turns. This I is the peak value of the inrush current. Here Ai by An and mu naught is approximately given to you in the calculations. Okay, so this is about the inrush current phenomenon in a transformer. So if you have any questions, we will meet in the meeting.